Good morning to my AP Chem students. I first want to apologize if I'm fumbling over my words. This is my third podcast I've made today, and I've already started this one over for you. So we're going to start with Chapter 14, talking about acids and bases. And I think at this point in your chemistry career, I hope that you recognize how important acids and bases are. Our body, a fine-tuned machine that our body is very regulated by acidity of our food that we eat, and in our blood, in our stomach, and how we digest. Cleaning supplies at home, hopefully you're using them. Do that tonight, help your parents out. Acid rain in our environment. Poor little goldfish. I think we're on Goldie the Fifth now or something like that. Joey keeps having some trouble taking care of his goldfish. And then in industry, fertilizers and polymers and steel, like we can go on and on and on how acids and bases are very, very important to the world that we live in. Now we're continuing equilibrium. So if you had a difficult time in Chapter 13, we're going to continue to build it in Chapter 14 and 15. So it's really the basis of AP Chem. You're going to get a lot of this on the AP exam. So I'm hoping that as we continue to walk down this avenue, things will get clearer and clearer for you. So the first thing we're talking about are Arrhenius theory. Savant Arrhenius. He was the first person to study the nature of acids and bases. And we should recognize that if we have an acid or a base, that they are going to ionize. And we know what ionize means, or dissociate. It's going to release a hydrogen ion and form the hydronium ion. You probably haven't heard of that in a while. H3O is the hydronium ion. And then bases, they ionize or dissociate also to release the hydroxide ion. Well, the Arrhenius theory did a great job for explaining acids. All acids have that hydrogen, they all donate that hydrogen, but not all bases have a hydroxide ion. You can go in your cupboard right now and take out some sodium bicarbonate or some baking soda, and that is not going to form a hydroxide ion no matter what you do with it. It's going to form a carbonate. So he could not explain that. Did not know about the formation of the hydronium ion, but that really wasn't as necessary in terms of trying to explain the base. So then we had two other chemists come along, Bronsted-Lurey theory. We have a Danish chemist, Johannes Bronsted, and an English chemist, Thomas Lorry, a little extra tidbit there for you. They really took the Arrhenius theory and made it even more general. And they said that an acid is just going to be a proton donor. And keep in mind that the hydrogen ion, if you think about it, hydrogen in itself has one proton, one electron. So if it now becomes an ion, are we basically just a single proton? Because it's lost that electron. There's not any neutrons, so really we are just talking about a proton ion here, or a proton. That's where it comes from. So the bases are accepting this proton and becomes a proton acceptor. So we have our generalized form right here. H we recognize as an acid, HA for the acid. We know that they are always aqueous, so we have the water there making a hydronium ion with the conjugate base, which would be without the hydrogen ion there. So if we want to show a specific example, you can see that we have water here. And if I were to draw the structure of water, you should recognize that it's a bent structure by now, has these lone pair of electrons here on the outside. That's a nice little drawing there. This is slightly positive side. This is going to be my slightly negative side of my water molecule. Then if I take a look at my hydrogen ion with my chlorine, you should recognize this as a covalent bond. And I do have a dipole moment here if we go back to Chapter 10, because these are not going to pull the same as each other. And if I take a look at this, I need to identify an acid or a base. Well, you might be saying to yourself, well, water can't ever be an acid, it always has to be a base. I'm going to show you some situations where it's actually amphoteric, when we get further into the chapter, that it can act in either direction. So that's why these are theories, because it's very hard to categorize every substance that we know. So if I draw out my hydronium ion, I have my oxygen here, and I have 3 hydrogens around the outside. It is an ion, so if you recall, we are going to put the brackets around it. It has a positive charge, still has a lone pair of electrons that are here. This is my hydronium ion. And then I have my chlorine ion, which has this lone pair of electrons around the outside. It is now completely stable as it's gained that one electron. So if I apply these theories, you can see that this has donated this hydrogen here. And so because it has donated, it is now going to become the acid. So this has become donated. This is accepting it. So this has become a proton donor. So this is going to be my acid, and this has become a proton acceptor. So that is going to be my base. Well, if we put these in pairs, you can see that this went with this, and then we have the water going to the hydronium ion. So because this is an acid, this makes this its conjugate base as its donated proton, the result of that, and this becomes its conjugate acid. We're going to work more with those and talk about the strength of them. And so you can see that in this transfer, we do have some acid-base pairs. And we can talk about now Ka. In our last chapter, we just talked about K as our equilibrium constant. And now we have Ka, which is going to be our acid dissociation constant. So we're going to do the same thing, you guys. If we take a look at our Ka for our above reaction, it would be the concentration of my hydronium ion times the concentration of my conjugate base, or my resulting root of my acid, over my concentration of my acid. And then we also have here our water. Now, water is really not going to play a part at all. It doesn't change the concentration, so you are going to omit that in your equilibrium expressions. You are never going to include the water. It's understood when you have an acid that it's an aqueous substance that it's there. That's not going to change our Ka value at all. And another shortcut way that you might see this, your book starts writing this just as an hydrogen ion to simplify things, times the conjugate base over the original concentration of the acid, and this is going to equal our Ka, our equilibrium constant for an acid. Okay, so that's where we're going to stop with this one. This is section 14.1. And try to keep these podcasts a little bit shorter. There's a lot of theory in this chapter. Oh, actually, sorry, I take that back. We are going to do one little review question in your book. So if you take a look at your book and open to page 625, and if we take a look at these examples, I just want you to see the proton donors here. So it says, write a simple dissociation ionization reaction omitting water, as I just talked about, for the following acids. So if we take a look at the hydrochloric acid, you can see that in the solution that they have taken that HCl and they have simply taken and dissociated that into a hydrogen ion and a chlorine ion. That's example A. Look at example B. Very, very similar. You should recognize that as acetic acid. Acetic acid is very weak. We're going to talk about how much these dissociate. So HC2H3O2 are acetic acid, so that hydrogen is going to dissociate. Then we look at 3. Here we have our ammonium ion. You may not look at that and recognize that it really is acidic in nature. Well, if I look at its resulting product, we have the hydrogen ion and we have ammonia. So you can see that this is donating, it's donating a proton, so that makes it acidic. And then I have my ammonia. And then if I look at D, you can see again, you probably won't recognize that as acidic in nature either. And it's C6, H5, and H3 with that positive ion there. And it's going to donate this ion. And when it does that, it's going to become more stable. That's why it does it. So I have my hydrogen ion, and then I have my aluminum ion that is now more stable because it does not have that excess charge of a hydrogen. Now, letter E starts with a complex ion. We have not talked about those. Those are ligands, and it looks pretty complicated, but what happens here is I have my aluminum, and it has the ability, because its spatial relationship, aluminum is in the 3rd energy level, that it has the ability to hold on to 3 waters around it. Well, if I'm donating a hydrogen ion, it should make sense to you that our hydrogen proton should make sense to you that it has to come from the water. And the only place that it can is it's going to donate from this hydrogen ion. And so I'm going to end up with a hydroxide, as you see as a resulting product that is written here in your book. So I have my donated proton, and then I have my aluminum, now with only 5 waters around it, with the OH, and now a +2 charge. Now these are complex ions. We have not talked a lot about them. They're thrown in, sprinkled in your book in every small little places. It's not like you would ever have to be able to write something like this. You would just have to be able to understand that, yes, the water was donating the hydrogen, and so because the hydrogen has a +1 charge, the resulting OH has a -1 charge. If you take a look at this resulting charge, it should make sense to you that that is a +2. You would never have to be able to write this other than to understand that this is called a complex ion, which hence it looks complex. All right, so read over that section, see if you have any other questions, bring them to class, and then we'll start the next section. Have a wonderful night.